In the syllabus, they given autocorrelation and then power spectral density, properties of white noise, then filtering through random signal through LTI system. So now we are going to see the properties of white noise. Before that, we'll see the properties of thermal noise. Then we'll see the properties of white noise. So last 10 minutes la mudichilla. Thermal noise. The another name for thermal noise is resistor noise, because usually this noise will be generated in the resistor of the circuit. So that's why this is resistor noise. Then or otherwise name of the inventor, that is Johnson noise. Okay, we have identified this noise, Johnson noise, or sometime it may be also called as white noise. But anyway, white noise we will discuss separately. White noise we will discuss separately, but mostly both are equivalent only. Thermal noise, resistor noise, Johnson noise, and then white noise. இப்போ தெர்மல் நாய்ஸ்னா என்ன? ரெசிஸ்டர்ல வர நாய்ஸ் வந்து என்னது? தெர்மல் நாய்ஸ். ரெசிஸ்டர்ல வர நாய்ஸ் வந்து தெர்மல். அதாவது நீங்க ஒரு சிக்னலை வந்து பாஸ் பண்றீங்க ஒரு பர்டிகுலர் சர்க்கியூட்ல, அந்த சிக்னல் வந்து ரெசிஸ்டர் வழியா போகும் பொழுது சிக்னல் மட்டும் இல்லாம சம் அதர் வேல்யூஸும் அது கூட பிக்கப் ஆகுது, இன்டர்னலாவே வந்து ஜென்ரேட் ஆகுது. That noise is called thermal noise. Actually, why the thermal noise is coming? What is the main reason for thermal noise? Okay, whenever we have a electronic component, say we are having thermal noise, we will be having some current. Okay, the current is due to the applied electric field or applied voltage. Then already this conductor and then these resistors will be having charges. Okay, the charges will be moving in a particular direction. Then only we'll get the current. Movement of the charge is called current. Then what happens when there is a temperature in the nearby areas? The temperature may come. The temperature may come to the device in any direction, in any three-dimensional direction. So temperature by default it will have its own energy. Okay, whenever the temperature is falling on the chargers, the charges will get some energy. Okay, from the temperature. So it will move in some direction depending on that. Say I am here, if I am getting some energy from this direction, then it will try to move like this. Then so what is happening due to this temperature, the effect of the temperature on the charges, okay, the charge tries to move in the random direction. Already we are applying voltage or electric field that makes the charges to move in a particular direction. Now suddenly due to the effect of the thermal power, the charges are trying to move in some other direction. That means it creates some kind of disturbance in the flow of charges. Okay, that we will consider as a noise. Okay, that we'll consider as a thermal noise. That means if temperature is more, the randomness, the movement of the randomness of the charges will be more, the thermal noise will be more. Okay, thermal disturbance will be more. When the temperature is more, disturbance will be more. That means thermal noise is more. When temperature is more, disturbance is more. Disturbance increases. Okay, it creates the disturbance in the movement. So thermal noise increases. Okay, so just quickly we have seen the effect of thermal noise is directly proportional to the temperature. Directly proportional to the temperature. Then whether is there any relationship with respect to the frequency of the signal? Usually the signal may have any frequency. Okay, the frequency may be 0 or it may be low or high, AC signal or DC signal. Again, whether the effect of this thermal noise is related to the frequency, that is another question. அதாவது லோ ஃப்ரீக்வன்சி அதிகமாக அஃபெக்ட் ஆகுது, டிசினா அதிகமாக அஃபெக்ட் ஆகுது, இல்லைனா ஏசி தான், அது போல ஏதாவது இருக்கா அப்படின்னு பார்க்கணும். ஸோ இன் ஜென்ரல் the effect of thermal noise is independent of frequency. In general, the effect of thermal noise is independent of frequency. That means what? Say I am at some frequency. My frequency can be anything, x-axis and then y-axis. In the y-axis, I am defining the power spectral density of this thermal noise. Okay, how this entire thermal noise power is distributed over entire frequency. Say this is Sx of f. Okay, so first I am operating at a 0 frequency. What is the effect of thermal noise. I am operating at say 1 kilohertz. I am operating at 1 megahertz, 1 gigahertz. What is the effect of this thermal noise? Mostly it is same. Okay, whether you operate at any frequency, that is not important. You can operate at any frequency. The effect of noise is not depending on at what frequency you are operating. So that means usually it is constant. Okay, the effect of thermal noise is independent of frequency. That means it is constant. Okay, so power spectral density is remaining constant. Okay, then usually that noise power usually depends on T. Okay, the noise power, say NP, I am defining NP. The noise power is directly proportional to T. The noise power is directly proportional to T. But I may be operating over some bandwidth. I may be operating with some bandwidth. Okay, some bandwidth. Say I am operating over this bandwidth. I am operating between these frequencies. Then this is the total noise power present in the system. Now I know what is this value and then this bandwidth. And this is the total noise power, or otherwise we can again, we have not defined what is y. We have not defined what is y. That y component we will define like n naught by 2. It is constant. Okay, that we are defining like n naught by 2. Okay, again quickly I will come back. What is n naught? What is n naught? Just for a moment, you just assume that it is like some number. N naught is some number. Again, I am putting instead of n naught, I am putting n naught by 2 because here I am using two-sided, both positive frequency as well as negative frequency. Or otherwise, if I am defining only with the two-sided power spectral density, two-sided power spectral density of the noise, then I know what. If I am using one-sided, I will use n naught. If I am using two-sided for representation, I have to use n naught by 2. That means positive frequency or negative frequency also you have to calculate. Then only you will get total power. Okay, so here, if it is one-sided, I will use simply n naught. I will use simply n naught. Two-sided na n naught by 2. So n naught தெரிஞ்சிடுச்சு. What is the bandwidth? இதுதான் bandwidth தெரிஞ்சிடுச்சு. Once if I multiply n naught into bandwidth, I will get the thermal noise power present in my system. Thermal noise power present, total thermal noise power present in my system. Okay, so thermal noise power, total thermal noise power, total thermal noise power that we are defining like P is equal to n naught into B. Okay, so what is n naught? N naught is the power spectral, one-sided power spectral density of thermal noise. Okay, what is n naught? Here we will define. N naught is the one-sided power spectral density of thermal noise. What is n naught by 2? Two-sided power spectral density. Two-sided power spectral density of the thermal noise. Then how to calculate that n naught? I know at what bandwidth I am operating. N naught we have defined like power spectral density. How to calculate that power spectral density? Say n naught. N naught is K multiplied with T. K is a Boltzmann constant. T is the operating temperature. Here K is the Boltzmann constant, that is 1.38 into 10 power minus 23